Hello everyone, good to see you again. I hope all you are doing very well. In this video, I'm going to talk about endogeneity and how to control for potential endogeneity in analysis using instrumental variables. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I'm going to first introduce endogeneity issues in analysis. Endogeneity is sometimes very critical, and there are various sources of endogeneity in practice. The reason why endogeneity can be critical is that endogeneity may lead to an omitted variable bias. As a solution, two-stage least square has been widely used in practice. It is also called IV regression because two-stage least square uses instrumental variables, for short IV. And I'm going to introduce the two-stage least square to solve the endogeneity problem. Well, using instruments has a problem when the instruments are weak. I'm going to talk about why weak instruments are problematic and how to check if instruments are weak in analysis. The key of IV regressions is to pick good instruments. Unfortunately, there's no rule of thumb for the choice of instruments. Instead, researchers have been relying on qualitative evaluations of instruments. So, I'm going to introduce several ideas of finding good instruments in the past studies. Last, I'm going to talk about an advanced topic related to incorporating heterogeneity into market share models. Alright, are you ready? Then, let's get started. Let me start with the linear regression model. Consider a linear regression of y on a binary variable d and a control variable x. Here, y denotes the outcome observed in data, and d is the assignment. Then, we already learned that the coefficient of d, delta, becomes the estimate of the treatment effect. But the estimate is unbiased only if the error is independent of the assignment. If the independence does not hold, the estimate of delta is biased because of the selection bias. Technically, endogeneity is defined in a regression as follows. All independent variables in a regression are assumed to be independent of the error of the regression. This is called the exogeneity condition in regression. If it is ensured that an independent variable is independent of the error, the independent variable is exogenous. If not, the independent variable is endogenous. Then, if the assignment D is endogenous, then the outcome is potentially correlated to the assignment, even if all of other control variables are clearly observed. That is, the exogenate condition in regression is identical to the conditional independence assumption, which is necessary for the unconfoundedness. If the treatment variable or assignment variable D is endogenous in regression, then the causal effect estimate, delta, becomes biased. There are variable regions that potentially lead to the endogeneity. First, if there are unobserved fixed effects such as seasonality and bread quality, the endogeneity may appear. For example, suppose that there is a firm that strategically prices its product to have more profits. So the firm charges a high price during the peak season, but a low price during the off-season. If there were no strategic pricing and seasonality, demand would go down as price increases. But due to the strategic pricing and seasonality, the observed demand is shifted. The demand with high prices is lifted up in data because it is highly likely coming from the peak season, and the demand with low prices is dropped because it mostly comes from the off-season. That is, in the true data generating process, the demand, Q, is given by the price, P, and the season, S. And the price is correlated to the season, although the price is uncorrelated to the error. Then, the price coefficient, beta, is the slope of the data by seasons. Now, let's see what happens if the seasonality is missing in the regression. This is the estimated regression. Compared to the true process, the error takes both the seasonal effect, gamma S, and the pure error, epsilon. Because the price is correlated to the seasonality, the price is also correlated to the error, E. However, the OLS finds the estimate, assuming that the price is uncorrelated to the error. So, the OLS estimate, B, captures the seasonality effect as well as the original price effect. Graphically illustrating, the OLS finds the slope value, B, without the seasonal labels. So, B, it becomes the slope of the line that passes through all data points, which differs from the true slope, beta. This difference is the bias coming from the endogeneity. Another source of endogeneity is unobserved demand and supply shocks. For example, consider the mask demand during the COVID pandemic. Before the pandemic, demand and supply generated an equilibrium at the intersection of the demand and supply curves. And the equilibrium is what was observed in data before the pandemic. But the pandemic generated a big shock on both demand and supply. On the demand, the need for masks significantly increased, so the demand curve was lifted up, and on the supply, the production costs increased, and consequently, the price increased. So the supply curve was shifted to the right, and the new demand and supply curves generated a new equilibrium. That is, in the true data generating process, the demand, Q, is given by the price, P, and the demand shock from the pandemic, eta. And the price is correlated to the demand shock because the supply was also affected by the pandemic. However, if the shock during the pandemic is missing in the estimation, then the error in the estimated regression, which is E, takes both the demand shock and the pure error. So the price is correlated to the error in the equation without the demand shock. But the OLS finds the estimate under the exogeneity assumption. The effect of the demand shock is captured by the price effect, leading to the endogeneity bias in the price coefficient, B. Graphically, if the demand shock during the pandemic is missing, the OLS estimate of the price coefficient, B, is given by the slope of the line passing through the observed equilibrium. And this slope is far from the slope of the true demand curve, beta. Another potential source of endogeneity is unobserved heterogeneity. The left side figure plots weekly beer sales and prices. As you can see, the trend line is upward, indicating a positive correlation between the price and sales. But the sales data were actually a collection of the sales from different stores. In the figure on your right, different colors indicate different stores, and for each store, the trend line is downward. That is, there is actually a negative correlation between the price and sales. And in the same manner, when heterogeneity across markets and individuals is missing in analysis, the unobserved heterogeneity potentially leads to the endogeneity in the regression and results in a critical bias in the price coefficient. The endogeneity bias can be described as an omitted variable bias. For example, if the endogeneity of the price is expected, then the price is expected to be correlated to the error. Let's divide the error correlated to the price into two components, eta and epsilon. And suppose that eta is the correlated part and epsilon is the remaining part, which is uncorrelated to the price. If the endogeneity is not considered in the regression, the error in the estimated equation, E, actually takes both eta and epsilon. And this error is actually correlated to the price through eta. However, as discussed multiple times before, the OLS finds the estimate under the exogeneity assumption. So, the OLS estimate of the price coefficient, B, captures both the original price effect, beta, and the correlation with the omitted eta. That is, if the endogeneity of the price exists due to an omitted variable, the price coefficient becomes biased, and the bias is proportional to the correlation between the price and the omitted. And we already learned about the omitted variable bias, and let's review what we've learned. There are no exact formula to compute the omitted variable bias, but we can roughly expect the sign of the bias based on the sign of the correlation and the sign of the omitted effect. If the omitted effect is positive and the correlation between the endogenous and omitted variables is also positive, then a positive bias is expected. If both are negative, then the bias will be positive. However, the signs are opposite to each other. The negative bias is expected. And the size of the bias depends on the size of the correlation and the size of the omitted effect. The higher the correlation, the bigger the bias, and the stronger the omitted effect, the bigger the bias. Then, the next question should be how to solve the problem. How to get the unbiased estimate of the effect expected to be endogenous. There are several solutions, but the most widely used one is to rely on instruments. Let's start with the same equation. Here, P is the endogenous variable, such as the price, and eta is the omitted variable, which is related to P. Now, suppose that there is a variable, W, such that it is correlated to P. Then, P can be described as a regression equation with W. Simply, suppose that it is linear, that is, P is given by pi times W plus U. Plugging this function into the original equation, we have a new equation with a term of W, minus beta times pi w and an error term E, which equals eta plus epsilon minus beta times U. Now, let's look at the correlation between W and the error. Epsilon is the uncorrelated pure error, so it is uncorrelated with W. And U comes from the regression of P on W, so it is also uncorrelated with W. Then, if the omitted variable eta is uncorrelated with W, then the error E in the new equation becomes independent of W. So, if there exists a variable like W, which is correlated to P but not correlated to the omitted eta, then the variable is called an instrument of the endogenous variable P. If we have a proper instrument of the endogenous variable, we can get an unbiased estimate of the effect of the endogenous variable through the two-stage least square method or instrumental variables regression. If the omitted confounders are not observable, that is, endogeneity exists, the regression is generally written as follows. And if there exists an instrument W, then W is correlated to the endogenous variable X, and W is uncorrelated with the error. The first condition is called the relevance condition, and the second one is called the exclusion restriction. Then, the unbiased estimate of the effect of the endogenous variable B can be obtained through the following regressions. First, regress the endogenous variable X on the instrument W. This is called the first stage regression. In the first stage regression, we can obtain the predicted value of X given W, which is pi times W. Then, replace the predicted X for the X in the original equation. That is, regress Y on the predicted X, which is given by pi W. This is called the second stage regression. In the second stage regression, we can obtain the estimate B for the predicted X, which is the unbiased estimate of the effect of X. Okay, so far, I have explained why endogeneity is critical, and I have introduced how to solve the endogeneity problem with instruments. The solution with instruments sounds very, very nice because we just need to find the proper instrument. Here's an example. Philip Wright study on the price elasticity of demand for butter. This case is known as the very first application of instruments. He fed a simple local of demand model to butter sales data. Q denotes the sales and P is the price. But his estimate of the log price coefficient was too small, and he suspected that there could exist unobserved shocks leading to an endogeneity problem. His solution was using weather as an instrument. Specifically, he used the amount of rainfall in the dairy region. His logic is as follows. If the amount of rainfall in a dairy region is lower than the average, then production costs increase, leading to an increase in the price of butter. So, the rainfall may be correlated to the price, that is, the relevance condition holds. But the rainfall in the dairy region does not directly affect the demand for butter in a market, which is usually far from the dairy region. This implies, although there is an unobserved demand shock correlated to the price, the rainfall is not correlated to the demand shock. That is, the exclusion restriction also holds. Well, finding a proper instrument is not that easy. Let me first talk about the relevance condition. The relevance condition can be quantitatively validated. One way for the validation is to compute the correlation coefficient between the endogenous variable and the instrument. The stronger the correlation, the less the endogeneity bias remains in the two-stage least square. Ideally, the correlation is expected to be high to get rid of the endogeneity bias. Another way for the validation is to compute the F statistics in the first stage regression. The stronger the correlation, the first stage regression becomes the more informative for the endogenous variable. The F statistics in a regression measures the informativeness. So, the higher the F statistics, the more informative the first stage regression. But the problem is that instruments are sometimes weak in terms of the correlation with the endogenous variable. If that's the case, the estimated effect through the two-stage least square is still biased. Here's an example of weak instrument problem. I generated data from this simple equation. The independent variable x is endogenous because it is correlated to the error epsilon. And I generated two instrument variables. One is correlating to x with a mild noise, and the other is slightly correlated to x with a huge noise. Of course, both were generated independently of the error. Then I fit the OLS and the IV regression to the simulated data. This is the result table, and please keep this in mind. The true value of the coefficient is minus 10. With the simple OLS, the estimate of the coefficient differs from the true value. That is, there exists an endogeneity bias. And when I use the variable with the mild noise as the instrument, the estimate is close to the true value. The numbers in parentheses are standard errors, so the estimate is statistically indifferent from the true value. The correlation with the endogenous variable is just 0.22, but the first stage F statistics is 52.6, which is usually very significant. But when I use the variable with a huge noise as the instrument, the estimate still differs from the true value. That is, the endogeneity bias still exists. The relatively big standard error says the estimate is statistically indifferent from the true value, though. The relatively big standard error also means a low statistical credibility of the estimate. And as you can see, the correlation with the endogenous variable is too low, and the first stage F statistics is also low. Although there exists a risk of weak instrument problem, we can handle the relevance condition by the quantitative validations. But the exclusion restriction cannot be quantitatively validated. The reason is very simple. The error is not observable in analysis, unlike the endogenous variable and the instrument. Instead, researchers have been relying on a qualitative supporting claim, such as a theory. Weather is one possible option as discussed, and there are several options of the instruments that have been frequently discussed in the literature. One is using wholesale prices as instrument for retail prices. Another is using product features as instrument for prices, especially for durable goods. Another is using prices in other markets as instrument for prices. This is called Hausman instrument. And another is using information of consumers in other markets as instrument for prices, such as demographics. This is called Waldfogel instrument. Now I'm going to briefly introduce each of those instruments. First, the wholesale prices. Retailers set retail prices given wholesale prices they paid to wholesalers. And in usual, a large portion of demand shocks on consumer packaged goods market appear at the retail level, not the production level. So the wholesale price is a good candidate of instrument. Park and Gupta used the wholesale prices as instruments in their study on the paper towel retail market. This table presents the correlation between the shelf price and the wholesale price of 4 major brands investigated in the study, and for all brands, they confirm the relevance condition. This table shows the endogeneity bias corrected. This red box indicates the estimate of the price coefficient under the exogeneity assumption. And this blue box indicates the estimate with the wholesale prices as instruments in 2 different model specifications. With the instruments, the estimate becomes much smaller, implying that consumers' price sensitivities are overestimated when the endogeneity is not controlled. Next, the product features. For durable goods, demand shocks on the market may be strongly correlated to the manufacturer prices, unlike the consumer packaged goods. Barry, Robinson, and Pix suggested to use product features as instruments for durables. Better product features usually incur high production costs, so the configuration of a product by features may be strongly correlated to the product price. But a product feature is directly related to the production itself, so the possibility of being correlated to the demand shocks is low. Thus, product features can be good instruments where both the relevance condition and the exclusion restriction hold. This table presents one of the results in their analysis. The row shaded in blue indicates the estimate of the price coefficient. The number in the first column is the estimate coming from the OLS estimation, and the number in the second column is the estimate with the product features as an instrument. Those numbers are quite different from each other, implying a potential bias due to the price endogeneity. In some studies, prices of the same good but in other markets were used as instruments. This type of instrument was suggested first by Hausman in 1996. So it is called Hausman instrument, and the underlying mechanism is as follows. Different markets may receive different shocks on demand. But for the same product, prices may not significantly differ across the markets because there exist various components in price shared across the market. Production cost is a good example. Thus, the prices of the same good in other markets are expected to be correlated to the price in the focal market, but independent of the demand shock on the focal market. Following Hausman's suggestion, Nebo applied Hausman instruments to his study on the market power in the ready-to-eat cereal market. He collected a panel data set of sales and prices across various cities over time. Then, he computed the average price excluding the focal city and used it as an instrument of the price in the focal city. This table presents the result from his analysis of the map, and this red box indicates the estimates of the price coefficient in 3 different OLS specifications where the endogeneity is not controlled. Those estimates are quite different from the estimates with the instrument in this blue box. The difference in the estimate strongly suggests the presence of the endogeneity. Last but not least, Waldfogel instruments. This type of instrument is similar to Hausman instruments, but it is using the information of consumers in other markets instead of directly using the prices. It is called Waldfogel instrument because Waldfogel first suggested it in 2003. Ing Fan applied Waldfogel's strategy into a study of the U.S. daily newspaper market. In this study, the consumer demographics in the competitors' market were used as instruments. Suppose that there are two counties, County 1 and County 2, and two brands, brand A and brand B. As in the figure, both brands are in County 1, but only brand B is in County 2. And we are interested in the price effect of brand A in County 1. Brand B is playing in both markets, so brand B's price is highly likely determined with consideration of demographics in both counties. And brand B is competing against in County 1, its price should be related to brand A's price. So, the demographics in County 2 is indirectly related to brand A's price. But the demand shocks on County 1 are coming from the people in County 1, not in County 2. So, the demographics in County 2 may not be correlated to the demand shocks on County 1. In that sense, the demographics in the markets where the focal brand is not, but its competitors are actively playing, can be used as instruments. So far, I have briefly introduced some instruments frequently used in the past studies. Now, I'm going to talk about a little bit different but related topic, the unobserved heterogeneity, especially for the market share model. As discussed, unobserved heterogeneity is a source of endogeneity, and there is a method to directly control for the unobserved heterogeneity. This method is sometimes called the BLP estimator because Barry, Robinson, and Pex first suggested this method in their 1995 paper I introduced. This method is usually used with instruments, but I'm not going to talk about the details of how to combine it with the instrumental variables approach. And this method is technically beyond this course, so I'm going to just introduce only the conceptual core in this lecture. Let me start with Barry's share inverse method that we used to derive the market share model. Utility for brand I is coming from the specific features of the brand, a demand shock on the market, and an idiosyncratic error. Psi I denotes the demand shock, and epsilon I is the idiosyncratic error for the brand. Then, assuming a logic specification, consumer's choice probability for brand I is given by this formula, which is a function of VI. VI is the utility excluding the idiosyncratic error. Using the share inversion method, the choice probability can be expressed by a linear form. The left-hand side becomes the difference of the log choice probability from the log choice probability for the outside option, and the right-hand side becomes VI. When it is applied to the market share data, the relative log market share is used as the market analogy of the difference in the log choice probability. In BLP's method, the preference on the product features is heterogeneous. For individual H, utility is still coming from the product features, the demand shock, and the idiosyncratic error, but the preference on the features, beta, is heterogeneous. Here, beta bar denotes the average preference, and individual specific preference, beta H, is added. Because individual level data are not observed, the individual specific preference cannot be directly inferred. Instead, it is probabilistically defined, and this P denotes the probabilistic distribution of the preference. And this beta H is sometimes called the random coefficient. In the same manner, the choice probability is defined by a logic choice. Now, the utility component in the choice probability, V, is given by a function of the random coefficient, beta H. Then, integrating out the choice probability over the probabilistic distribution of the preference, beta H, we have an analytic prediction of the market share for brand. And comparing the analytic prediction to the observed market share, the preference parameters can be inferred. For the past decades, BLP's method has been updated by various researchers. One notable update is a work by Waldfogel and Brandenburg in 2009. Let's take a look at the data generating process of the market shares. Each individual consumer makes a choice over time. The choice made by a consumer is aggregated at each time period, and this aggregation, denoted aggregation 1 in the dotted vertical box, generates the market shares at the time period. And the shares are observed over time, being the main data source of the market share model and BLP's method. But we can also think of another aggregation across time. Aggregation 2 in the dotted horizontal box denotes this aggregation. The individual consumer's choices over time are aggregated, resulting in a distribution of consumer purchase stats. For example, annual market reports provide the proportion of consumers who have bought or used the brand at least once per year. Albuquerque and Brandenburg suggested to use both of aggregation. And the additional aggregation allows for more accurate inference of the unobserved heterogeneity of the preference on product features. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, an online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.